Okay, welcome back everyone. Happy Monday morning. I hope you all had a good weekend. I'm going to continue our discussion. I made all the homework problems available, and I hope you were able to access them. Any questions as we continue? Okay. I still haven't made up the exam yet, so I really can't tell you any more specifics on that. But again, I think the homeworks and the lecture concepts, if you follow them and the manipulations we've done in class, you should be able to follow. You should be able to do well on the exam. Okay. So I'm going to continue where we left off yesterday, Friday, and if there are no questions, and we were looking at adiabatic reversible volume change, a process that's adiabatic and reversible using an ideal gas equation of state, fluid that's modeled by that equation of state. And here I've shown what this would look like on a pressure volume diagram. It's just a qualitative curve, but we see that pressure, volume, and temperature all change in this process. And I've noted here that temperature in the adiabatic process changes. Okay. And we did our first law analysis to arrive at the relationship between temperature and volume initially. So initially we considered temperature and volume because those were the two variables that naturally fell out of the first law analysis. If you remember, du is equal to dq plus dw, and since it's adiabatic, dq is 0, and since it's an ideal gas, we can write du as cv bar dt, and then dw, because it's reversible, it's just minus p temperature volume dv. Okay, and so temperature and volume were the two natural variables that fell out of our first law analysis of this process. Okay, that's why we initially had a relationship between temperature and volume, and that relationship is given here. Okay, in different forms, where we have the natural log of the ratio of temperature and volumes related in such a manner through this gamma parameter, which is the ratio of the specific heats of ideal gas in the constant pressure and constant volume case. So gamma is just a parameter that we define. It's nothing that is an absolute thing. It just falls out of your analysis, and so we just write it that way for shorthand. Cp for an ideal gas is given by 5/2 R. It's a constant for an ideal gas only, and Cv is 3/2 R. So Cp is higher, as we would expect, because there's no volume change during a constant pressure process. Because there's a volume change during constant pressure process, the system does work, and so Cp is larger relative to the Cv case, where you have constant volume. So you don't lose anything in a constant volume process through work. And that's why Cv is lower than Cp. And this is in general for most fluids. And so the ratio then for gamma turns out to be 5/3, and we see that it's greater than 1 right here. Okay, and so these are the expressions, again, we have for our relationship between temperature and volume related through gamma. And since we have the log of something on the left and the log of something on the right, and I'll call natural log just because I don't want to say natural log all the time. So if the logs of two things on either side of an equal sign are equal, then the things in the arguments of the log are equal. And so the log relationship can actually be written as T2/T1 is equal to B1/V2 raised to the gamma minus 1. Okay, and so that really gives us this relationship between the temperatures and the volume. And so we did this last class. It's nothing new, it's just a review. But we can extend this relationship now to include pressure, and we can relate pressure and volume. And that's rather simple and straightforward because we know that the ideal gas equation of state is PV equals nRT. And so we can solve for temperature in both cases, the initial state and final state. And so what we find is T1 is just P1 V1 over NR, and T2 likewise is same relationship with 2 instead of 1. So the ratio then of T2 over T1 using these expressions just turns out to be this guy. So T2 over T1 is just P2 times V2 divided by P1 times V1, the product of pressure and volume. Okay. Any questions, comments? Okay. So P2 over V2 times P1 over V1, which is T2 over T1, is related to V1 over V2 raised to the gamma minus 1 in this step, where all I've done is replace the ratio of this guy here. Okay. And so now what we can do to go from here to here is to isolate P2 over P1. And we do that by multiplying by V1 over V2, both sides. And what we have on the right-hand side then, right here, is just this thing with V1 over V2. And we know that when we have something that has different, if we're multiplying something with different exponents, all we do is keep that thing and then just add the exponents. So in this case, the exponents are 1 and gamma minus 1. So 1 plus gamma minus 1 is just gamma. And so the ratio of P2 over P1 turns out to be V1 over V2 to the gamma. Very easy, very simple. Okay, that's given here. And I can write P2 over P1 right here. Okay. So in this line, then I just rearranged P2 over P1 is V1 raised to the gamma divided by V2 raised to the gamma. And now what we can do is put all the terms with the subscript 2 on one side and all the terms with the subscript 1 on one side of the equal sign on the other side of the equal sign. And that gives us this. Okay. And what we see here is that P2 times V2 raised to the gamma, where only V2 is raised to the gamma, not P, just the V, is equal to P1 times V1 raised to the gamma. Again, only the volumes are raised to the power gamma, not the pressures. And since we have initial state parameters equal to final state parameters, it shows us that something is conserved. And what this indicates is that the pressure times the volume only raised to the gamma constant is equal to constant. Okay, so P times V, where only V is raised to this gamma parameter, is equal to a constant. Only for a process where you have a fluid that's modeled as an ideal gas, and the process is adiabatic and reversible. So these are our major conclusions then for an adiabatic reversible process right here. Okay, so these were the relationships that we found applying the first law to the adiabatic reversible process of an ideal gas fluid. Okay, and so here we have it summarized. So these are the final results. Okay, and so it's just keep in mind that P V raised to the gamma is equal to a constant. And again, only volume is raised to the gamma, not pressure. Any questions on that? Comments? All right, it's rather straightforward, I think. We'll make use of that later when we talk about the second law. So PV is constant along a reversible adiabat. So let's consider now for a comparison, an isothermal process for an ideal gas. And this is rather simple, actually. So we want to get a relationship in terms of this product of PV or something like that, something analogous to this for the case of an isothermal process. Okay. And this is rather easy because we know that PV is equal to nRT for an ideal gas. And if temperature is constant, then this side is just constant. Okay, it's just constant for an isothermal process. Therefore, we can write PV is equal to a constant when we have an isothermal, and I'll just say iso-T process for ideal gas. Okay, so we see here PV is equal to a constant when we have isothermal, whereas up above, we had P times V raised to the gamma as a constant when we have adiabatic and reversible. Okay, any questions? That the isothermal case is rather simple. Okay, so PV is equal to a constant. And so we can say that P2, P1 is equal to, let's see, what would that be? V1 over V2 for the isothermal case. Okay, and that's just because P2, V2 is equal to P1, V1. PV is a constant. Any questions or comments? Okay, so let's see what these two look like. And both of them we're going to say are reversible, okay, because they're reversible. Okay, so I should reversible. Okay. They're both reversible. So let's plot these. Okay, so what do they look like on a PV diagram? Okay, so we can have our pressure and our volume as our y and x axes. So this can be V1, and this can be V2. Okay. But we're going to have to compare the cases where we have an adiabatic and an isothermal process. So they're both going to start from V1. So we can just let that be here. Okay, so where we have P1, V1, T1. Okay, but we're going to compare the adiabatic and the isothermal process. So we're going to have two different final volumes. Okay, and I want to discuss why. Perhaps somebody already knows why. So what happens in the adiabatic case? Do we have a temperature change? So let's say we're going to expand. So let's just consider we have expansion. Okay, and we start at P1, V1, T1, and we're going to expand. Okay, and so if we have an adiabatic process, we know that the temperature changes and the gas expands. So what do you think happens to the temperature as the gas expands in this process?
It decreases.
Right, the temperature decreases in the adiabatic process. T goes down, okay? And in the isothermal, what happens to T?
It's constant.
Right, T is constant. So in one case, the temperature goes down, and in the other case, the temperature is constant, okay? So based on what you know about how temperature and volume are related, if you have a gas expanding, and this is just thinking about an ideal gas, what would you say about the final volumes in the adiabatic and isothermal cases, knowing that in one case the temperature falls and in the other case temperature is constant? And so how would the two volumes, so V2, right? We have two volumes because we have two final volumes V2 because we have an adiabatic process and an isothermal process, and these two processes are different. And they're different in that in one case, temperature falls, in the other case, temperature is constant. So what would V2 adiabatic be in terms of magnitude compared to V2 isothermal? Does anyone want to hazard a guess, knowing what you know about this?
Would it be
It
the
would be
same?
Well, several people answered. Can you repeat your, I think I got different responses.
I said it would be the same.
Okay, any others?
it would be smaller
Ah, okay. So the person who said smaller, why?
because T and V are proportional.
Okay, that's right. And so in one case, temperature is lower than the other case. And so the volume would have to be lower, right? So this is the relationship between V2 adiabatic and V2 isothermal, okay? Does everyone see why? Because if you have a temperature drop in one case, the final volume will have to be less than in the case where you have no temperature drop, okay? So in both cases, we're going to the same final P2. We'll have the same final pressure. So the pressure doesn't matter in this case. Okay, so we're both, so here's P1. So in both cases, we're gonna go to P2. Okay, that's our stipulation. So that's something that we can do by having a weight on our piston or whatever as this thing expands. And we have the final pressure is going to be the same in both cases. So, and I kind of made a mistake here. Let me oh no, that's V1, that's fine. So let's do this. I'll make V2 adiabatic here. And I'll make V2 isothermal here. Okay, because we know that V2 isothermal is larger. And so what these curves look like then is that and we know that the same pressure exists at the second state for both of them. So we'll have P2 for the isothermal case here, P2 for the adiabatic case here. P2 are the same. And so what the process looks like then for the adiabatic case is something like this, okay? And then for the isothermal case, we have, so is that curve going to be steeper or a little bit more shallow compared to the adiabatic case on this plot? So we're going from the black to the blue line, point, from the black point to the blue point. And so if we compare a curve that I would draw, do you think it's going to be shallower or is it going to be steeper than the red curve? Meaning the slope. Is it going to have a higher slope in general or is it going to have a lower slope?
Higher slope.
Why?
Because the T is constant.
Okay, so let me draw the curve. Maybe then that'll help you. It's not a straight line, it's a curve. Now what would you change your mind about the slope of the two lines? Which one do you think has a higher slope?
Adiabatic.
The adiabatic, right? Because why? Both of these curves has the same delta y. I mean, the easy way to think about this is slope is equal to delta y over delta x. Both of these guys have the same delta y. Okay? But in one case, delta x is bigger than the other. So the denominator is bigger in one case. So in that case, the slope would be smaller. Again, this is speaking in a general sense, not exact, because you know that the derivative is, and the slope is a point-by-point entity. It's a point-by-point beast, so we really can't generalize it. But you see here that the isothermal process has a smaller slope in general than the adiabatic. And we're going to make use of this. So that's why I'm presenting this here on this plot. Okay, when we look at the Carnot cycle, as we begin our study of the second law, we're going to be using adiabatic reversible processes and isothermal reversible processes for an ideal gas. So this is a bit of a teaser for what we're going to be moving into, and this is why I'm presenting this here. Okay, so the two slopes here are very important to keep in mind. One for the adiabatic case, one for the isothermal. Both are reversible, and this is for an ideal gas. Okay, and so let me just kind of write that down here for you so you can remember. So this, again, is for an ideal gas. Okay, it's reversible. Everything is reversible. That reversible process is very useful. Okay, now hopefully you're beginning to see that. So it's reversible, and in one case, it's adiabatic, and in one case, it's isothermal. Okay, so these are all the stipulations that we have for this graph. Okay, any questions or comments, or anything you want further clarified? No, nothing? Okay, I'm going to move on then. And we're going to do an example of a process or several processes. Okay, so here's an example. And this is putting everything together. There's a lot of stuff now in this example that we're going to put together. And so let's see. Let's do this problem. So here we have a pressure volume diagram, okay? And I think if you understand a lot of the things here, you'll be in good shape for the midterm, okay? Not everything, of course, I can't guarantee everything, but if you can follow this discussion, you know, you should have some confidence. And I'm just giving you some feedback here, constructive feedback. Okay, so let's consider a few processes for an ideal gas. So let me just say that we have an ideal gas. Okay. So that's our equation of state. Very simple. Okay, and everything, unless stated, is reversible. Okay. And so now I'm going to draw a few processes here. So let's start here. Okay, so this will be P1, T1, and V1. Okay, and then we will go to a point here. Okay, and this will be P2, V2. Oh, no, sorry, that should be P3. Okay, you'll see why in a moment. So this is P3, T2, and V2. Okay, so we're going to have a process here that looks like this. Okay, it's not a line, it's a curve, and we'll be going in this direction. So it's an expansion. And I'll tell you that this is a reversible. Let's see, we'll make this process B. Okay, and so B is adiabatic. Okay. Any questions? Okay, so that's an adiabatic process. Now I'm going to put another process called C, and C is going to go from here to this point in this direction. And so this will be another point, this red dot. Okay. And that is going to be, as you'll see in a moment, P2. That's why I had a P3 for the first one. So that's going to be P2. This is going to be T1, V2. Okay, so it's V2 because it's a constant volume process. The arrow goes straight up, so volume doesn't change. So if we start at this point, the point P3, T2, V2, if you go straight up, then the volumes don't change. Okay. The pressures do change. So since we were initially at P3, now we're at P2. And we were initially at T2, now we're going to go to T1. And that's kind of interesting because that first black dot was a T1. We had P1, T1, V1. So what I must be doing now is going to introduce an isothermal process where temperature doesn't change. So the next and final process I'm going to introduce is an isothermal process where you go from this state, okay, and you're going to go to this point. So that's going to be, oh, and you know what I did? I did not write. So this is path C right here. Okay. The first path I introduced, the adiabatic path, was B. C is our constant volume. Okay. And then finally, the blue, which I'm going to label path A, is going to go also in this direction. Okay. A is going to be isothermal. Why? Because it goes from T1 to T1. And you see here that it has a smaller slope, just as we saw here. The isothermal has a smaller slope compared to the adiabatic. Here, the blue, which is isothermal, has a smaller slope compared to the adiabatic, which is black. Okay, so these are the three processes that we want to sort of consider here. Okay, does everyone got the picture down? Okay, and we'll only consider 1 mole of an ideal gas for the moment. It doesn't matter. You can always scale it up. So we look at a process for 1 mole and we can always scale it up. All right, so let's look at the processes A, B, and C individually, and let's compute all of the things that are associated now that we've learned from the first law and enthalpy. So we have all of these functions, U, right? So far, we've been exposed to U, Q, W, and H, and their differentials. So, you know, we have their total differentials. Remember, dq and dw have these lines. Okay, so this is all we have. And so we can now ask to compute all of these guys for these various processes. So let's do it. Let's jump in. So first, let's do A, which is the isothermal case. So here, A is isothermal. Okay, and of course, it's reversible. All of these guys are reversible for the ideal gas. So we know that for an ideal gas, du is only a function of, for an ideal gas, u is only a function of T. Okay, and this is from the Joule-free expansion experiment. I introduced this idea that for an ideal gas, u is only a function of T, not a function of V. And we can write du as CV ideal gas dt. Okay, but if dt is 0, because of isothermal, you know that du is 0 for this case, right? And if we integrate from point 1 to point 2 for the isothermal case, delta U is going to be, if we integrate,
0.
Yep, exactly. There's nothing there. So we have delta U is 0. And here, what I should have said is we want delta U and delta H and Q and W. Q's and W's don't have deltas, only the state functions U and H. So for this isothermal case, it's very simple. The other thing we saw that H of ideal gas, the enthalpy, is also only a function of temperature from the Joule-Thomson experiment. Okay, that Joule-Thomson coefficient is 0 for an ideal gas. So eta Joule-Thomson for an ideal gas is equal to 0, if you recall. That means that dH is equal to Cp of an ideal gas, dt, but we know that dt is 0 for the isothermal case. So dH, in this case, is equal to 0. And if we integrate, delta H is going to be, of course, 0. Now, was that clear? So we have delta U and delta H. So here we had to apply a couple of concepts, right? The first law and the fact that we have this guy and this guy. Okay, so these are conceptual things that we've integrated to come up with the answer to the question of what delta U and delta H are for this process for an ideal gas. Any questions? Okay. So now we can address Q and W, okay, for this process. So we know that du is 0, which means that dq plus dw is going to be 0. And so then dq is equal to minus dw for this process. But we know what that is because that's just going to be that, because it's reversible. Remember, we said this is a reversible. Everything here is reversible. Oops. So that's pretty simple. And so dq, which is equal to minus dw. Actually, I made an error, right? dq, which is minus dw. What should I have here instead of a minus sign?
Plus.
Yeah, exactly. So it's dq is minus dw. It's plus p dv. And p is just nRT. We know T is a constant because it's isothermal, dV over V. And we can integrate so Q is going to equal the integral of dq from state 1 to state 2. That's just equal to minus the integral of dw from state 1 to state 2. And that's just equal to the integral of nRT. T is a constant, so I can pull it out of the integral dv over v from v1 to v2. So we're going from v1 to v2. But that's pretty obvious. That's just going to be nRT. And that t is really t1. So we can write t1 here. Remember, we start at t1 and we keep t1, as we see in this plot. So that t is really just t1. And this will just be log of v2 over v1. And so that gives us q and w for this process. There you go. So we have our 4 results. Any questions? Comments? So I think we have everything, right? Yeah, du, dq, dw, dh. Yep, 1, 2, 3, 4. Okay, let's move on if there are no questions. Let's do the next easy one. That's this constant volume process, which is C. Okay, let's do the C process. So let's do process C, which is in red. Okay, so this is process C, which is constant volume. And so for this constant volume process, we're going to go from P3, T2, V2, P3, T2, V2 to P2, T1, V2. Okay, so P2, T1, V2, that's the process. It's constant volume, so we know already dW, which is equal to minus, and it's reversible, so minus dW, which is equal to P dV. This is going to equal 0, So W for this process is equal to 0. I think that should be quite, I don't think I have to spend too much time on that for the constant volume process because dV is 0. Okay? Okay, so now let's see what we have here. This is an ideal gas. Okay, so we know that du for an ideal gas is just CV bar, ideal gas dt. Okay, it only depends on temperature, right? This is what we found through the Joule free expansion. CV ideal gas is a constant. So integrating delta U, which is just U at P2 T1 V2 minus U at P3 T2 V2 is just the integral of CV ideal gas dt from T1, from T2 to T1. Okay, we're going from T2 to T1. Okay, this just turns out to be CV ideal gas times T1 minus T2. So that's delta U. And here we had to apply the fact that ideal gas, for an ideal gas, U is just a function of T. That's what we had to apply. That was the concept that we had to apply for this problem. Okay. We can do the same with delta H. We know that dH is only a function for an ideal gas of Cp, of the heat capacity. And so to get delta H, we just integrate. So delta H is going to equal the integral from T2 to T1. Cp is a constant. So that comes out of dt, and that's just equal to Cp ideal gas times T1 minus T2. Any questions or comments? And so now we have to get, let's see, we have W, we have delta U, we have delta H, Q. But that's kind of simple because we know that du is equal to dq plus dw. dw is 0 because it's constant volume. So du is equal to dq. And if we integrate, we know that delta U is going to equal Q. And so Q is equal to whatever delta U is, and that's just CV ideal gas, T1 minus T2. Okay, so we have everything. Right? Any questions or comments? Okay, and so that now leaves us with what? The adiabatic process B. Okay, now we're going to look at the adiabatic process where it goes from T1 V1 to P3 T2 V2. And that's adiabatic and reversible. Okay. So process B, adiabatic and reversible for an ideal gas. Okay. And it goes from P1 V1 T1 to P3 T2 V2. Let me make sure. P3 T2 V2. Yep. Okay, so that's the process we're looking for here. So let's see. Make sure I do this correctly. Okay, it's adiabatic, so we know already dq is equal to 0. That means q is equal to 0 if we integrate. That's easy for adiabatic. So now let's see what we get with our first law analysis here. Well, we know that from du is equal to dw, okay, because dq is 0. But this is interesting because now we don't have only volume changing, but we also have temperature changing. If I were to just write this as minus P of TVN dV, this integral for an ideal gas is going to equal minus nR T over V dV, okay? But this problem is a little bit tricky because temperature is not constant. I can't simply do an integral that involves integrating over the volume dV, because in this case, temperature and volume change. Remember, T1 goes to T2, V1 goes to V2, okay? But that's okay, that's okay. So we can't get work directly, but we can actually get work indirectly through U, because we know for an ideal gas, du ideal gas is only a function of temperature, so that's just going to be CV ideal gas dt. And we can get delta U just by integrating this very simple equation with knowing that CV bar ideal gas is constant. I already showed you that that's 3 halves R. Okay. So delta U, in this case, is just going to be CV bar ideal gas times, what's the temperature change? T2 minus T1. Okay, so we have delta U. There we go. Delta H is going to be the same, and I'm going to let you fill in all the only difference is going to be that you have CP bar instead of CV bar. Okay, again, that's only because if you have an ideal gas, U and H are functions of temperature only. And so we only have to worry about temperature change, which is going from T1 to T2. Well, we know that work and U are related right here, right? So W, for this case, is just equal to delta U. And that's just going to equal CV ideal gas T2 minus T1. There you have it. Okay. Now, if you were given numbers, then all you have to do is plug in the numbers for everything, and you would get numerical values. But in this example, I wanted to show you how we would generate the solution with equations, because that is what the solution is: equations. You can't run away from that. And so now it would just be a matter of plugging and chugging with numbers on a calculator if you were asked for numerical values. Any questions or comments? I think this was a very straightforward application of the first law to some processes using ideal gas. I'll just take a few seconds. Any questions, comments? Because I want to do one final thing before we leave for today. So, okay. What I want to do, if there are no questions, finally, as we leave, a parting thought here. And it's related to this process, those 3 processes. Is a parting thought. We know that all of the processes, and this is important, are reversible. Okay, that was what we stipulated at the beginning of this discussion. That's what we chose, and that's okay. We can choose that if we want. Okay? Even though it's an idealization, we can choose it to be that. It helps us solve problems, at least to get some solutions, and then we deal with cases where things deviate from those solutions, but we know why. So all of these processes are reversible. So what I want to look at is this beast. Okay, so let's consider this beast, and I haven't motivated it for you, but I'm just going to introduce it, okay? And for the moment, we're just going to see what happens to it. So let's consider this beast. And the beast is this thing called dq, and we know it's reversible. All of the steps here are reversible, so I'm going to write reversible here over t. I'm going to create some beast. It's a mathematical function. This beast really is a mathematical function. But don't be intimidated. It's very simple. Okay, so don't really be intimidated. It's just something, all right? So it's called dq reversible over t, and it's labeled reversible because all of the steps here are reversible, obviously, okay? It's nothing profound. And so what we're gonna do is compute this guy for each of those processes, okay? And so let me remind you what the processes are. We have an adiabatic, B is adiabatic, A is isothermal, and C is constant volume. Okay, so let's go with the adiabatic case first, because that's the simplest one. In the adiabatic case, dq is 0, right? And so for the adiabatic case, which is step B, here's our parting thought here. For step B, the integral, and what we're really after is the integral of dq reversible over t, okay? For each of these processes, we want the total. We want everything total, okay? We can start with the differential form, and then we integrate to get what we want. So for process B, this integral of this beast, dq reversible over t is 0. Why? Because dq reversible is equal to dq adiabatic, and that by definition is 0, so we don't have to worry about it. Now let's consider C. Okay, process C, and we want dq reversible over t for that. So let's go back. Process C is the red one. That's that vertical constant volume process. Okay, so let's see what our analysis gave us for that process, the red one, for constant volume, for dq. Okay, so in this case, we saw that dq is equal to du. Does everyone follow, right? For that red process, because there was no work. So dq is equal to du. And this is an ideal gas, so du is just Cv dt. So let me write that here. Okay. For this case, du, since we have an ideal gas, is Cv bar ideal gas dt, and that was equal to dq. Okay, and that was because dw is 0 for C. It was the constant volume process, so we have dq is equal to Cv ideal gas dt. Now let's, using this guy, let's create our beast. We know it's reversible. I could have put a reversible here. All of these processes are reversible. So let's create our beast for this case. dq reversible over t is just going to be Cv bar ideal gas dt over t. Okay, so that's all I did, taking this equation, right, which is for dq reversible over t, and then all I said was let's divide that by t. And so what we get then, the integral, so now we can just do the integral, right? So this is going to be the integral of dq reversible over t. Cv is a constant. That's just going to give me the integral of dt over t. And what are the temperatures here? From T2 to T1, I believe. Right? Yeah, T2 to T1. So this is just Cv bar ideal gas, natural log T1 over T2. That's what this integral of dq reversible over t turns out to be for that process. That is the red one. Okay, did everyone follow? Now let's just finally do the blue one, which is the isothermal case. So that was the isothermal case where we went from P1, V1, T1 to P2, V2, T1. Okay. Again, we want to consider this dq reversible over t beast. So let's go take a look at what we had for the blue process. For the blue process, let's see. What did we have for dq? Well, dq was equal to dw right here. And it was dq is equal to dw or minus dw because du is 0 for this case. It's isothermal and it's an ideal gas. Okay. That's this concept of U only being a function of temperature for an ideal gas. That's why we could write this guy. So dq is equal to minus dw. Okay, so let's kind of start with that. dq reversible then is minus dw over t. Okay, but we know that minus dw is just going to be p dv. We lose the sign. Okay. And so T1 is constant, all right? So what do we have here? Let's do the integral. P is equal to nRT over V. And we have a T and a dV here. That's what this integral of dq reversible over T is, right? So what I've done here is introduce nRT over V. And of course, it's really T1. So I have to put a T1 there and a T1 here. And the T's cancel. So what I'm left with is nR. Let's see, this is going to be dV over V. And we're going to go from V1 to V2. Okay. And so the integral of this dq reversible over T is equal to nR natural log V2 over V1. Okay, everyone see how that happened? So we have this beast, dq reversible over T, integrated for each one of these steps, A, B, and C in this process. Okay. I've run out of time. So what I would like you to do before next class is find this out. And I'm not going to tell you what it means, but I'm just going to, you know, as part of your review for the midterm, okay, I want you to find this. And you should know now what this integral with this circle means. Okay, we've computed dq rev over T for these three steps in the process. So take a crack at this before next class, and this will help you with the review of your midterm as well. Okay, so see what you can do with that. And I will post the lecture so that you can have the results we have. Any questions, comments? Sorry I went over. Okay, great. I wish you all a good week. I will be here for a little while now for my office hours if you need, and there will be the discussion session on Wednesday. So I'm going to end the meeting now, and again, thanks everyone for your participation.
Thank you.